presentation on the physics of the welding arc, we will be looking into the various aspects related with the arc, like the electrical aspects affecting the heat generation in the different zones of the welding arc, the way by which arc is initiated for the welding purpose, and the need of maintaining the arc so that the heat generated by the welding arc can be used for melting of the fine surfaces. And at the same time we will also see that how the arc length affects the heat generation in welding arc and other aspects. So, as far as content is concerned in this presentation, we will be looking into the electrical aspects of the welding arc, initiation of the welding arc and the methods which are used for initiating the welding arc, and the important conditions which are necessary to maintain the welding arc, and then arc characteristics, which is basically about the relationship between the arc voltage and the welding current, and when the arc length is changed, then how the relationship between the arc voltage and the welding current is changed, and what is its effect on the heat generation and the performance of a particular welding process as far as development of the sound weld joint is concerned. So, if we see here in the electrical aspects, we know that the flow of current is important for stabilizing and for having a smooth welding arc, so that the heat can be generated for melting the fine surfaces. But when the current flows, the gap between the electrode and workpiece mainly acts as a impedance for the flow of the current, and this resistance for the flow of current results in the generation of the heat. Here the impedance for the flow of the current in the welding arc is influenced mainly by the density of the charged particles and the way by which they are moving in the arc gap. The higher is the density, easier will be the flow of the current, and greater is if, and similarly if the greater is the mobility, better will be the flow of current. So, if the charged particles are uniformly distributed between the electrode and the workpiece, then the impedance between the electrode and workpiece in the gap will be uniform, and accordingly for a given flow of current the generation of heat will also be uniform. But it has been observed that the distribution of the charged particles in the radial and axial directions in the welding arc is not found uniform, and accordingly the impedance varies along the length from the electrode tip to the workpiece and from the center of the arc to the outer surface of the arc. And therefore, because of the variation in distribution of the charged particles in radial and axial directions, impedance is affected, which in turn affects the heat generation in the different zones, varying from the electrode tip to the workpiece or from the center of the arc to the outer surface of the arc, and accordingly temperature variation is observed in the arc zone. So, three main zones have been identified and which are commonly observed based on the kind of a voltage drop takes place in the arc, and these zones are cathode drop region and cathode drop region, plasma zone and the anode drop region. And the reasons for the voltage drop in these three zones have already been explained in the previous presentation, but the voltage drop in each of the region affects the heat generation associated with that zone, and the product of the difference, potential difference across the arc and the welding current gives the total power of the arc. So, when we multiply the arc voltage, which is basically the difference in the voltage across the electrode tip and the workpiece, and the welding current which is flowing between the electrode and workpiece, giving the developing the arc, and the product of these two arc voltage and the welding current gives the power of arc, and it governs the amount of heat being generated by the arc in unit time. Here the arc voltage is obtained from the sum of the voltage drop in the cathode drop region, plasma region and anode drop region. we will see in the next slide, this arc voltage here is considered as a sum of the potential drop across the cathode drop region, which is termed as Vc, designated as Vc, and voltage drop across the plasma zone is designated as Vp, and the potential drop across the anode drop region is designated as Va. And the sum of all these three, the voltage drop in these three zones, that is Vc, Vp and Va, forms the arc voltage. And when this arc voltage is multiplied with the welding current, we can obtain the power of arc, which directly indicates the amount of heat being generated. So, here you can see the power of arc can be obtained from the sum of the arc voltage, which is the sum of the voltage drop in cathode drop region plus voltage drop in the plasma region plus voltage drop in the anode drop region multiplied by the welding current. Here we can see that the typical electrode, this is the electrode tip, and the region very close to the electrode, that is cathode, is the cathode drop region indicating the voltage drop Vc, and the slightly away from the cathode drop region and the anode drop zone. Here in between we have the plasma region indicating the voltage drop in the plasma region Vp, and the anode drop zone having the voltage drop of the Va. So, sum of these three voltage drops in the three different zones gives the arc voltage. So, to if we see the equation in of the equation which is used to determine the power of arc, having the arc voltage multiplied by the welding current, and this arc voltage is composed of the voltage drop in the three different zones. This equation suggests that the distribution of the heat in the three different zones, that is cathode drop region, anode drop region and the plasma zone, can be changed by varying. If these voltages are affected, then the voltage drop is also arc voltage is also affected. So, in order to regulate the heat generated in the three different zones for a given welding current, it is important to change or to regulate the voltage drop in the desired zone, whether it is a cathode drop zone, anode drop zone or the plasma zone. For example, if we increase the arc voltage drop in the cathode zone for a given welding current, then the heat generation in the cathode drop zone will increase. And similarly, if the voltage drop in the anode drop zone is decreased for a given welding current, the heat generation in the anode drop zone will be reduced. So, if we see that the distribution in these three zones, distribution of the heat in the three zones can be regulated by varying the voltage drop in a specific zone for a given welding current. And the factors that affect the voltage drops in the particular zone is influenced by the number of the factors. So, if we see in totality, the arc voltage drop between the electrode and workpiece is influenced by the three main factors. One is the arc length, the second is the shielding gas, and the third is the use of the low ionization potential elements and their amount present in the electrode coating. And this third factor basically affecting the ease of availability of the free electrons required for initiation and maintenance of the arc. So, if we see here, in general, if the arc length is increased, then the arc voltage increases, but this increase in arc length primarily increases the voltage drop in the plasma region because of the increased gap between the electrode and the workpiece, while the shielding gas, if change of the shielding gas affects the ionization potential of the gaseous medium between the electrode and workpiece. So, the gases having the higher ionization potential, they will be offering the higher arc voltage, and therefore, the selection of the shielding gas affects the arc voltage. For example, instead of the argon, if the helium is used, which offers the higher ionization potential, results in the higher arc voltage under the identical welding conditions of the gap and the current. Similarly, if the low ionization potential elements are present in the electrode coating, which are providing easy release of the electrons for initiation and maintenance of the arc, then the presence of the free electrons in the large quantity and in the large number between the electrode and workpiece decreases the impedance and facilitates the easy flow of the current, which in turn decreases the arc voltage. So, the presence of the low ionization potential elements and the use of the shielding gas, means the type of the shielding gas and the arc length, affects the arc voltage in total, that is the difference means arc voltage between the electrode tip and the workpiece. But the each factor has a specific effect on the cathode drop zone or the plasma zone or the anode drop zone. If we see here the effect of each of these factors on the variation in the voltage drops in a specific zone. The variation in arc length, as I said, mainly affects the arc voltage drop in the plasma region, and accordingly heat generation in the plasma region is influenced, and basically increase in arc length increases the distance between the electrode and the workpiece, and which directly increases the plasma zone size or the length of the plasma zone, and which in turn increases the resistance for the flow of current between the electrode and workpiece, and that is why the voltage drop in the plasma region increases, which in turn increases the heat being generated in the plasma zone. While the shielding gases, the selection of the shielding gas affects the heat generation in cathode and the anode drop zones, because it affects directly this factor is directly affected by the ionization potential of the shielding gas, and those gases which offer higher ionization potential, they result in the higher anode or cathode drop zones, means higher drop in the voltage in the cathode and the anode drop regions. The addition of the low ionization potential elements like sodium and potassium in the electrode coatings or in the flux reduces the arc voltage, because these elements provide the easy release of the free electrons after the ionization in the arc gap, and the presence of the large number of the charged particles in the arc gap decreases the resistance for the flow of current and increases the electrical conductivity, and which in turn reduces the resistance for the flow of current, and so the arc voltage decreases when the low ionization potential elements are used with the electrode coatings. So, if we see here, the arc voltage is affected by the various factors like arc length, shielding gas, low ionization potential elements, and and accordingly the heat generation in the arc gap is affected, because arc voltage multiplied by the welding current directly gives the power of arc, which indicates the amount of heat being generated, which will be generated in unit time. The generation of the heat and heat at the anode and the cathode is primarily governed by the welding process and the polarity. If we see for a given flow of the welding current, the variation in anode voltage and the cathode voltage directly affects the heat generation in these zones, but how to regulate the amount of heat being generated in the anode and in the cathode side, that can be done easily by changing the polarity. With the change of polarity, electrode which was cathode earlier can be made anode, and the workpiece which was earlier anode can be made cathode. So, the change of polarity affects which side will be the anode or cathode, and accordingly heat generation will be regulated. So, and similarly the amount of the welding current which can be used, that primarily depends upon the size of the electrode which is being used and the type of welding process in question. So, for regulating the heat to control the amount of heat generation, it is important to see that what kind of polarity can be used associated with a particular process. For example, the TIG welding, when used with the argon as a shielding gas, offers offers the higher current capacity when the DCEN is used, that is when electrode is made negative as compared to the situation when the electrode is made positive, because when electrode is made positive, the tungsten electrode tends to melt because of the high heat generation in the electrode side. So, that is why when the TIG is used, normally it works with the low welding current, and the tungsten provides the easy release of the electrons, and these two factors in turn result in the low arc voltage, and the working with the low welding current results in the low heat input, and that is why the TIG in general is known as the low heat welding process. But the amount of heat generation generated in the anode side or in the cathode side, that is either in the workpiece side or in the electrode side, can be easily regulated by using the proper polarity. With the TIG welding, normally it is required to have the generation of the less heat in the electrode side, so that the tungsten electrode does not melt and it remains and there for long, means it so that it offers the longer life, and that is why with the tungsten inert gas welding, it is common to use the DC EN polarity, and so that less heat is generated in the electrode side and more heat is generated in the workpiece side for melting of the fairing surfaces. While in case of the submerged arc welding, the lot of heat is generated by use of the high current, but when the DC EP is used, that is electrode is made positive. So, heat generation in the large amount at the cathode side, that is in the electrode side, results in the higher melting rate, and which in turn results in the higher deposition rate by the submerged arc welding process. So, now if we see that in case of the submerged arc welding process, the application of the electrode positive polarity, that is the DC EP, generates the more amount of the heat in an electrode side and facilitates the high melting rate as compared to that of workpiece. So, the use of the DC EP results in the higher melting rate of the electrode, so the higher deposition rate and the higher welding speed. If we see these two aspects, that is the polarity and the welding process, the TIG works with the low welding current, and the use of the DCEN results in the low heat to have the longer life of the tungsten electrode, while in case of submerged arc welding, to generate more amount of heat, electrode is made positive, and the use of the high welding current associated with the submerged arc welding results in the higher melting rate of the electrode, and which in turn offers the higher deposition rate and the higher productivity of the submerged arc welding. So, the heat generation is directly influenced by the welding current, the kind of polarity which is being used, and the welding current is dictated by the welding process which is being used. However, apart from the current and the polarity, the other factors as described earlier, the arc length, the presence of the low ionization potential elements, and the shielding gas also affects the heat generation in the arc gap. So, to look into the greater detail that how arc length affects the various aspects related with the arc welding, if we see that increase in arc length basically increases the potential of the arc because of the increased loss of the charge carrier by the radial migration to the cool surface of the plasma. So, if we see here in this diagram that if we have one electrode and the arc is established between the electrode and the workpiece. So, here to have the smooth and stable arc, it is necessary that there is sufficient presence of the charged particle in the arc gap, and more the number of the charged particles are present in the arc gap, better will be the conductivity and easier will be the flow of the electrons. If this gap is increased, then it will decrease the charge particle density, and a decrease in the charge particle density in turn will increase the resistance to the flow of the current, and increase in the resistance to the flow of current will increase the voltage. So, and this the decrease in the density of the charge particles in the arc gap mainly occurs due to the increased losses of these charge particles from the arc surface, and this is one reason that these charge particles are lost to the surroundings from the arc surface. And the second one is that the arc surface, because of the increased arc length, the loss of heat from the arc surface increases with the increase of the arc length. So, this increased loss of heat increases the decreases the temperature, and decrease in temperature decreases the number of charged particles because of the reduced thermal decomposition possibilities, which contribute significantly in generation of the charged particles in the arc gap. So, there are basically the two reasons, one is the heat loss, decreasing temperature, this is one, and the second one the loss of charge particles from the surface of arc. So, because of the reduction in temperature of the arc zone due to the heat loss from the arc surface to the surrounding, and the reduction in the number of charge particles in the arc zone with the increase of arc length, the charge particle density decreases, and the decrease in the charge particle density in the arc gap increases the resistance to the flow of current, and increased resistance to the flow of current increases the arc voltage. So, this is one simple thing which happens with the increase of the arc voltage. So, now we will see that increase in spacing between the electrode and workpiece generally increases the potential of the arc because of the increased loss of the charge carriers by the radial migration to the cool boundary of the plasma, and the increase in arc length of the arc column further exposes the more surface area to the low temperature atmosphere, which in turn results in the lot of heat losses to the surrounding, and it leads to the loss of the charge carriers to the atmosphere, and this these losses of the electrons from the arc surface must be accommodated to stabilize the arc by increasing the arc voltage. So, if arc voltage is not increased, then it becomes difficult for to maintain the flow of current. So, automatically with the reduction in density of the charged particle due to the losses of the charged particles to the surroundings and reduction in temperature of the arc voltage is increased automatically. So, the most of the heat generated in case of the consumable arc welding process goes to the weld pool, which in turn results in the higher thermal efficiency. This is the another aspect, like when for a given welding current, when the arc voltage is increased, this in case of the consumable arc welding processes results in the higher thermal efficiency, because thermal efficiency is about the heat is being generated in the arc, what fraction of the heat is actually being used for melting of the Fieng surface and melting of the filler material, so that the fusion weld can be produced. In case of the consumable arc welding process, the heat generated in the cathode side is also used for melting of the consumable electrodes, and the heat generated in the anode side is used for melting of the workpiece. So, the heat generated in the both anode side and the cathode side is effectively used for melting the electrode as well as to the workpiece, and both these heats are effectively used for melting purpose and for the development of the weld joint, while in case of the heat generated in the plasma is not effectively used even in case of the consumable arc welding process. And therefore, the thermal efficiency offered by the consumable arc welding process generally becomes higher than that of the non consumable arc welding process. Now, we will see that with the change of the welding process, how the welding thermal efficiency is affected, and the great difference in the thermal efficiency of the welding process or the arc efficiency of the welding process is found in case of the consumable and a non consumable arc welding process. To understand this, if we see here, if there is a non consumable arc welding process where electrode does not melt, then the arc is established between the electrode and workpiece, where workpiece melts because of the heat of the welding arc, but the electrode does not melt because of its non consumable nature, but the heat generated in the same way in 3 different zones, that is the anode drop zone, heat in the plasma zone, and heat in the cathode drop zone when especially DC En is used, means electrode is made negative and workpiece is made positive. In this situation, the heat generated in the cathode drop zone is given by Vc into I. So, this heat in non consumable arc welding process is not used. Similarly, the heat generated in the plasma drop zone given by Vp is also not used for melting of the base material. Heat generated in the anode drop zone given by Va into the welding current is, this is the only portion of the heat which is effectively used for melting of the Fieng surfaces and to develop the weld joint. So, if we see the heat generated by heat of the arc, if we see here, so there is no scope for cutting. So, heat generated in arc is given by V into I, where V is the sum of V includes Vc plus Vp plus Va. So, only this portion of the heat, or in this portion of the heat is not used effectively in case of the non consumable arc welding process, while the heat generated due to the anode drop region due to the voltage drop in the anode drop zone is used in case of for melting of the base material. While in case of the consumable arc welding process, heat generated in the cathode drop zone, heat generated in the anode drop zone, both are effectively used, and that is why the arc efficiency which is given from the ratio of the heat being used in the anode drop region divided by the heat generated in the welding arc, this gives the arc efficiency for non consumable arc processes, while the arc efficiency for consumable arc welding processes is given by Va into I plus V C into I divided by V I, and because of this use of the heat generated in the cathode drop zone and the heat generated in anode drop zone, use of both these heats for melting of the Fincke surfaces and the electrode results in the higher arc efficiency of consumable arc welding processes than the non consumable processes, and this is the main reason behind the low thermal efficiency of the tungsten inert gas welding process or the plasma arc welding process as compared to that of the shielded metal arc welding, submerged arc welding process. So, we will see further that how the thermal efficiencies of the vary with the nature of the welding process. Here we can see the most of the heat generated in the consumable arc welding process goes to the weld pool, which in turn results in the higher thermal efficiency of the consumable arc welding process. Similarly, the thermal efficiency of the metal arc welding process is also found higher than the non-consumable arc welding process like TIG. In case of the non-consumable arc welding process, efficiency is found lower, say 40 to 60%, while in case of the metal arc welding process and submerged arc welding process, thermal efficiency is found 70 to 80% and even higher than the 90% in case of the submerged arc welding process, because most of the heat generated in the anode drop zone, plasma region and cathode drop zone is used for melting of the Fincke surfaces of the base material and for melting of the consumable electrode. So, now we will see that to apply the arc welding arc for effective melting of the Fincke surfaces and develop a weld joint, it is necessary that it is initiated in a proper manner and a stable arc is maintained, so that the continuous and the uniform heat can be generated for development of the sound weld joint. So, the various approaches are used for initiating the welding arc, and the two are very commonly used for initiating the welding arc, that is the touch start method and the field start method. And the application areas of these two methods to initiate the welding arc are different. In touch start, invariably electrode is brought in contact with the workpiece to initiate the arc, while in case of the field start, the high potential difference between the electrode and workpiece is established, so that electrons are released and the flow of current starts from the electrode to the workpiece, and the arc is initiated. Maintenance of the arc is a different issue. We will look into the greater details of the methods which are used for initiating the welding arc. If we see the former method, that is the touch start method, is used for all common manual welding process, where electrode is brought in contact with the workpiece to initiate the arc, while the later one, that is the field start method, is preferred under the conditions when either the manual operations are not there, that is either the semi automatic or other automatic welding processes are used. So, where the manual intervention or the manual interference is to be avoided, then the consumable arc welding, then the field start is used like in automatic welding processes. And also in the situations where we do not want to have the contact of the electrode with the workpiece, to avoid any kind of contamination of the weld pool from the electrode material due to the melting, like it is commonly observed that when the tungsten electrode is brought in contact with the workpiece, in case of the TIG welding process, melting of the small amount of the electrode tip transfers the tungsten particles as an inclusion in the weld joint, and which acts as a site for the weakness to the weld joint. So, under those situations where we want to avoid the contact of the electrode with the workpiece, under those situations also the field start method is used, and it is common to use the field start method when the automatic welding operations are required to be performed. The manual operations are normally, for the manual operations normally touch start method is used. We will see that how each the arc initiation method works in. In case of the touch start, electrode is brought in contact with the workpiece and then it is immediately pulled apart, and so that very small gap is created between the electrode tip and the workpiece. If the gap is too big, then again no arc will be initiated. This small gap, maintenance of the small gap just after pulling it apart from the workpiece is important. Once the electrode is touched and just as soon as the electrode touches to the workpiece, the flow of current starts from the electrode tip towards the workpiece, and under this condition short circuiting takes place, and under the short circuiting conditions, when electrode touches to the workpiece, the flow of a heavy current starts, and the flow of heavy current results in the excessive heating of the electrode tip and the base material surface. So, excessive heating of the electrode tip and the base material results in the partial melting first, and even slight evaporation of the electrode tip material takes place. So, generation of the molten metal and even in a very small amount, and even generation of the metal vapors at the electrode tip is produced, and all this short circuiting followed by partial melting and even evaporation of the electrode tip material takes place very quickly in very short time, within a fraction of the second, and once this happens, electrode tip is pulled apart, and as soon as the gap is created, the potential difference between the electrode tip and the workpiece is established, and once the difference is established, because of the thermal ionization, the ions are released by the thermal decomposition of the metal vapors and by heating of the electrode tip. So, the presence of and these in turn results in the presence of a small amount of the charged particles in the gap between the electrode tip and the workpiece. This circuit diagram basically shows that the two plates which are being welded and the electrode is connected to the power source, and the workpiece is also connected to the power source, and when the electrode is brought in contact with the workpiece, short circuiting takes place. The flow of current through the electrode tip to the workpiece results in the heavy flow of current, which in turn results in the partial melting of the electrode tip material and base material, and even some evaporation also takes place. So, this heating and the evaporation results in the thermal ionization of the metal vapors and the electrode tip material, and these two phenomena results in the production of the charged particle in the arc gap. Once the charged particles are produced and the potential difference established between the electrode and the workpiece because of pulling a part of the electrode from the workpiece results in the flow of current, and once the flow of current starts through the charged particles, for a moment arc is developed. This arc will extinguish if the sufficient conditions are not met. So, the maintenance of the arc is the another aspect, but just to initiate in this approach, electrode is brought first in contact with the workpiece and then it is pulled apart. This in turn results in the short circuiting for a short while, which in turn develops a lot of heat, and the development of heat causes the thermal ionization as well as the dissociation of the metal vapors to produce the charged particles, and this ionization of the metal vapors becomes easier than the atmospheric gases because of the lower ionization potential of the metal vapors. So, the production of the small amount of the metal vapors in the gap between the electrode tip and the workpiece also facilitates the easy release of the electrons in the touch start method. This method if schematically it has been shown, when there was a heavy flow of current results in the generation of the metal vapors and the thermal ionization, and the thermal ionization of the electrode tip material and the thermal ionization from the metal vapors results in the charged particles in the gap between the electrode and workpiece, and establishment of the sufficient potential difference between the electrode and workpiece results in the flow of current through the gap and the arc is initiated. To use the heat of the arc for the welding purpose, it is necessary that whatever arc has been developed and initiated, it must be maintained, so that a smooth and stable arc can produce the heat uniformly for melting of the fairing surfaces and so as to develop the weld joint. The field start is the another method which is mainly used for the automatic welding processes or those processes where we want to avoid the direct contact between the electrode and the workpiece. In this method, basically high strength electric field is applied between the electrode and the workpiece, so that the electrons are released from the electrode surface, and these electrons provide the required number of the charged particle between the electrode and workpiece to initiate the flow of the current. The development of high strength field for ejection of the electrons from the cathode spots is important feature of this method. Once the free electrons are available in the arc gap, establishment of the normal potential difference between the electrode and workpiece causes the required flow of the current through the charged particles to initiate the welding arc. In this case, no contact between the electrode and workpiece is made to have, which can lead to any kind of the contamination of the welding arc from the electrode material, and that is why this method is effectively used for the automatic welding processes, and where we want to avoid any kind of contact between the electrode and workpiece. Schematically in this diagram we can see the high potential difference between the electrode tip and the base material is established, so that the electrons can be released from the surfaces of electrode and the base material for initiating the arc, and once the electrons are released, these are accelerated and moved. Moving will result in the secondary emission as well as ionization of the gases present in the arc gap. So, this is how in case of the field start method arc is established. So, in this presentation we have seen that the different electrical aspects related to the welding arc and their role in the generation of the heat, and what are the various factors that affect the heat generation in the different zones of the welding arc, and how to regulate the heat generation in the specific zone in order to get the higher deposition rate and the development of the sound weld joint. Apart from the electrical aspects of the welding arc, we have also seen that the two methods of initiating the welding arc, these are the touch start and the field start, the basic principle of the touch start and the basic principle of the field start, along with their other field of applications. Now, in coming lectures we will see the characteristics of the arc and their role in the development of the sound weld joint. We will also see that how arc can be maintained, so that heat can be uniformly generated for the consistent and smooth weld joint, and we will also see that what are the different types of the forces which are generated in the arc region and how do they affect the metal transfer in the weld region and development of the sound weld joint. So, thank you for your attention.